Dynamics, here we come. Let me welcome you back to another video about dynamics. Yes, now we are dealing with examples. I have prepared for you 4 examples, guys, the rocking ones. Then I am thinking that I might have a bonus example. It's what I'm planning. But if that does not happen, okay, of course, it was just being planned. It was not a guarantee. So we will have these 4 examples that we will be dealing with. Let's start with the first one. Let's read it. A train with a mass of 150 megagrams. Now we have a different term there, megagrams. I wonder what it means. Mega is actually a million. So if you want to change it to kilograms, and kilograms is the measurement that is used for a mass, and a kilo is in thousand, so a million divided by 1,000, which will give us 1,000. That will mean 150 megagrams is equal to 150,000 kilograms. So let's continue reading now that we understand this. A train with a mass of 150 megagrams is attached to a locomotive with a drawbar. The train is uniformly accelerated from rest. That means u is equal to 0 initial velocity. On a horizontal track, this is another trick, because now we know that we are dealing with it that starts from rest, and it is on a horizontal track, so we'll use the horizontal formulas. Then it says the resistance to motion. What is the resistance to motion? The resistance to motion is Fr. So we have Fr right there. So the resistance to motion is 6 Newton per 6 Newton per megagram of the mass of the train. So what does that mean? You remember when you were dealing with beams in statics, when you wanted to change the UDL into a point load, what you will do, you will multiply the force of the UDL, because for example, let me say that it was given as 3 kilonewtons per meter and the span of the UDL is 4 meters. Obviously, we will say 3 times 4. That means 3 kilonewton per meter times 4 meters. Then the meter and the meter will cancel out. Then we'll be left with newtons only, or kilonewtons only. The same thing is happening here. We'll say 6 Newton per megagram times 150 megagrams, so that the megagram and the megagram will cancel out, and then we'll be left with only Newton, because remember, resistance to motion is Fr, and Fr is a force. Forces are measured in newtons only, not in newtons per megagram. So that is what we have learned so far. Then it goes on to say the force in the drawbar is 33 kilonewtons. Obviously, this is your Ft. Now we have with us Ft, we have mass. So we have Ft, we have mass, we have Fr, we have U, and we know that the conditions are for horizontal movement. Alright, then let's see how we're gonna do this. The first question says calculate the force to accelerate. Alright, let's go straight to the formula sheet and find out how do we know, or how to get the force to accelerate? When you come to our formula of change, we can see acceleration force is equal to ma. We have the mass, but we don't have acceleration. That means we need to get the acceleration first. So we had that, but when we come here, remember the conditions are horizontal. When we come here, we can see that we do have Fa equaling Ft minus Fr, and we have Ft, and we also have Fr, or we can get Fr. So this is the ideal formula for us to use. But let's check if under the horizontal, yes, horizontal for acceleration, we talked about horizontal, we talked about acceleration, here we do have that formula, so we can simply use that formula. So, but let's first find our Fr. So this is our Fr. As we said, we'll say 6 times 1/5 will give us 900 newtons. Now Fr is in newtons. We can therefore look for Fa. We know Ft is there. We know Fr is this one. We calculated it. So we can just subtract them and get their difference. So we have our Fa right there. Okay, now we will move to the next line. The acceleration of the train. The acceleration of the train. Okay, since we do have Fa, I think we can have acceleration. Remember, when you go to our formula sheet, Fa is equal to ma. We do have m, we do have Fa, we only need a. So we can use this to find acceleration on the horizontal plane. So that's what we get. Fa is equal to 3200, ma is equal to 150,000, a is what we need. So we managed to get our a as 0.214 meters per second squared. So we answered the second question. What about the third question? Third question wants the work done over the distance of 2 kilometers. Now we know that the work done is equal to force times distance. Now we are given the distance being 2 kilometers. So which force can we use? Because we have three forces here. We have Ft, we have Fr, we have Fa. So which force can we use to find this work done? Okay, let me tell you, all the time you should go for Ft, unless they are saying we need work done against friction, which we can see when we are dealing with this thing, because this is work done against friction or against resistance to motion. That means we'll use Fr for this work done. So it will be Fr times the distance. So that is the only exception. Otherwise, generally we will always use Ft as our force. So we have a work done being equaling our work done equaling Ft times S, which is 2 kilometers. Obviously, this is our work done, 66 megajoules. What about the next question? It says time taken. Now we are looking for time. That's what we are looking for. Time. isikhathi baba, ixesha. Then let's go on and find our time. Which formula can you use to find the time? We can come to this one. This does have time. We have initial velocity, we have acceleration, we have s, so we can find time right there. I think this, in fact I know this one will give us time. Then let's see. Yep, we substituted and got our time. Then let's see what is the next question. The power required. Now we are looking for power. Kimatla, amandla, that's power. So the power, obviously we can use the famous formula for power being force times velocity, but we do not have the velocity, which is the final velocity in this case. We do not have it. Or we can use the, let me check another formula for force. We can use the force as work done over time. Do we have time? Yes, we just calculated time. So we have work done, we have time, so we can get the power. So this is the time, this is the work done. Let's find the power. That's it. So this is the end of the first example, and I tried to make it very simple in terms of explaining the statement thoroughly, so that when we come to calculations we just flow. As we did, we just flew when we were doing our calculations. Thank you very much for your attendance. God bless you. Till next time. Hola! Let me welcome you back again to yet another example for dynamics. Example number 2. Let me read the question. An engine exerts a force of 35,000 Newton on a vehicle and draws it up an incline of 1:120 against a resistance of 60 Newton per ton. This, or the mass of the engine and the vehicle, is 240 tons. We need to calculate the acceleration of the vehicle. Alright, now let's analyze our statement. Let's analyze the terms that are important to us. Number 1, we have that force exerted by the engine, that is Ft. We have Fr right here. And we have the mass. Obviously Fr will equal to, remember what we said before. We said that Newton per ton times ton will give us newtons only. So this will be our Fr when you multiply those two, just as we usually do on UDL. We do have the ratio right there. Yes, I'm right. We do have the n incline there, the ratio of an incline. That means that is our sine theta. So sine theta is equal to this. That's what we have. We just analyzed what we are seeing on that question. Okay, now let's go to explain the term turn. Now they are saying 240 tons or tons. Now what does ton mean? Ton means 1000 kg. So ton basically is the same as megagrams, because ton equals to 1000 kg, megagrams equals to 1000 kg. Basically ton and megagrams are exactly the same in magnitude, so they are one and the same thing. Then let's continue trying to explain what we are talking about. Since we can see that we have an incline in our mind, we have this diagram because this is an incline. But this time we are told that an engine exerts a force of that while it draws it up. So they also told us that it's drawn up. No wonder we have Ft on that side, because it's being drawn up and incline. Okay, now as we know that mg sine will always going in that direction, that means down the slope. Mg sine is going there. So what are we gonna do with this boy? First things first, we know that we need to calculate the acceleration. The formula that has the acceleration, let's look to our list of formulas. The one that has acceleration is this one. So we need Fa to find acceleration. We already have the mass, but we don't have Fa. So we can find acceleration from Fa. Then let's go for it. Can we find Fa? Oh yeah, we can. That's Fa under the incline. Okay, let me just go back a little and show you where did I get that Fa. We have acceleration. We are asked to find acceleration. That means acceleration is expected to be there. So it's not a constant velocity, there is acceleration. And then we're told that it's up and incline. So this is the formula for up and incline. So we can use this formula right there, or we can just use that one with Fa added. Alright, that is it. Then we can do our substitution. We have 35,000 for our Ft, and Fr is the product of those two, and mg, obviously this is m, which is 240,000 times 2, which is 9.8. Remember, sine theta equals to 1/120. So that is sine theta. So this is basically what we have: Ft, Fr, mg, then that is sine theta. 1/120 is sine theta. So we have this for our calculations, and then we can just press that on a calculator. That's the answer. Nice one. Makes sense, doesn't it? Then we have our Fa. Now we come back to the formula where we know that we'll get the acceleration, substitute by those values, and then we get our acceleration as small as that one. That's about it with example number 2. I hope it does make sense, because I spend some time explaining these terms, everything that I think is new to you here, so that you may not struggle. Now, some people may have a question: where is 1:120? Okay, remember, 1/120 times mass times g is equal to this thing. So 1/120 is this one. When it's underneath the line, it's already 1/120. Okay, thank you very much, guys. See you on the next example, in fact the third one, and I love you. God bless you. I'm not sure if you will understand this example without a diagram, because I noticed that I didn't do any diagram for it, but I hope I will explain it in such a way that you will make sense out of it. So let me again welcome you to a dynamic problem or dynamic examples. This is example number 3. It reads as thus: a train starts from rest on a top of a 2% incline. Now our incline is given as a percentage. So that means sine theta is equal to 2 over 100, or simple 1 over 50. That is our sine theta. It's an incline and runs. Let me also underline it so that you can know that. So this is sine theta. So we continue by saying a train starts from rest. So we also have our u equaling 0. From rest on the top of a 2% incline and runs 1,2 kilometers down the incline under the force due to gravity only. So that means Ft is not there. The resistance against motion is constant at 50 Newton per ton. Now we are familiar with this. Calculate the velocity of the train at the foot of the incline after 1,2 kilometers. We are familiar with this. We have our S, so that is the S that we have. That is the distance that we have. Now they are saying calculate the velocity. So we need the velocity. That's what we are looking for, the velocity. Calculate the velocity of the train at the foot of an incline after 1,2 kilometers by making use of the law of conservation of energy. I think when you see the law of the conservation of energy, you have only one formula in your mind, or maybe two. But there is a formula that is in your mind when we talk about the law of conservation of energy, because we were told that we will talk about the law of conservation of energy regarding potential energy and kinetic energy. So that's the formula that's in my mind already when I see this. Let the mass, or we're given the hint as well, let the mass of the train be m kg. Alright, this is our hint, so we can use it to find what we want. Now let's go to the list of formulas. Obviously it's not here when we, it is here, it can be here. So we have EP equaling mgh, we have EK equaling half mv squared. Then we have work done, because I can see that we do have the frictional force, so we can use the frictional force as well. But to be specific, this formula is the one that we are going to use. We have EP being mgh, we have EK being mv squared over 2, we have WR, or work against friction, being FR times S. We have FR and we have S. So we have everything we can be able to calculate, that the only thing we do not have is M, which is the mass. So let's go and see how are we going to attempt this. Then we have the distance or the height. Remember, the height is equal to for example, we have this slope, that's the angle. Then in that slope we have this distance being s, and that s is the one that's equal to 1,2 kilometers. So then at the top we will have our h, which is, then at this side this is the angle. So we have the angle, we have s, we have h, and we have the slope. So if you have the angle, the h and s, which is the hypotenuse, and you are looking for h, then opposite of a hypotenuse is equal to sine theta, isn't it? So that means sine theta is equal to h over 1,2 kilometers, and 1,2 kilometers is equal to 1,200. So h over 1,200 is equal to 2%, because we said that will be our sine theta. Sine theta will be the ratio for this one. Then if you want h, remember we have h over this, so you'll multiply this to your sine theta. So that means this is your sine theta, this is your h, you're multiplying, this is your s, you're multiplying it to it, then you are getting your h. So this is how you will get the h for this problem. I think it does make sense. If it does not make sense, please rewind, otherwise it will make sense. Okay, or let me restart everything. We will restart everything. Okay, let me restart again. As I've said, I am restarting this whole thing once more so that we can understand it much better. We said a train starts from rest. Oops, I was not supposed to cancel it. I was supposed to just underline from rest. Yeah, from rest. It says it starts from rest. Then we are given the slope in the form of a percentage, which is our sine theta. We have s right there as 1,200 meters. We are told that this is an incline and there is no force that has been applied. That means there is no Ft, the resistance against motion. That means this is resistance against motion is Fr. Obviously there is our Fr. Then we have we need to calculate the velocity. That's the question. It wants us to find the velocity at the foot of the incline after we have finished s. We are told to use the law of conservation of energy, and we are also given the hint that m is equal to, the mass is equal to mkg. With the information that we have, obviously we may think that we need to start by to find m, but you will see this is actually helping us. This hint is actually helping us. So let's start with the FR. FR has m in kg, yet here we have tons. So that means we know that tons equals to 1000 kg. So in other words, we can just write 1000 kg right there. Okay, then we know that it says from rest we have the slope of 2%, and that slope of 2%, that means this is a triangle, and now I have drawn the triangle in a better vision for you guys. So that is our triangle. We have S, we have H, we have theta. We know that sine theta is equal to 2%. 2% means 2 over 100. That means it's equal to 1 over 50. That is 2%. Then we also know that S is equal to 1,2 kilometers, which is 1,200 meters. Now sine theta is equal to H over S. Then we can make H the subject of the formula. When we make H the subject of the formula, this is what we get. H is equal to 2 over 100, which is our sine theta multiplied by S. So that's what we are getting, because S was dividing H, so when it crosses the equal sign, it will multiply the sine theta. So that's what we have there. So therefore our H turns out to be 24 meters. All right, that's what we have with H. The next thing that we can deal with now is this FR. We have dealt with 1,2. We know that it's an incline, and we know that the resistance against motion is this. Now we can deal with that, and this goes because they told us the law of conservation of energy, so we know that this goes with what we have here. Law of conservation of energy, we have only two formulas there, this one, and this is the one that we'll use because we are given the frictional force for calculating the work done against friction. So we can quickly go on and deal with that one. This is how I did it. Work done against friction will equal to force, frictional force, and the frictional force will be 50 over ton. Ton is equal to 1000 kg, so we have 50 over 1000 kg. Then we are multiplying this 50 by mkg. Then kg and kg will cancel out. We are left with no kg at all. That's what we have for FR. What about S? S remains the same, 1200, still the same as 1200. So this 1200 is for S, this part is for FR. That's the part. So when you multiply those two, you get 60 times mass joules. So we have the second answer there in joules. Then now we can come to our formula, because we need velocity. We are asked to calculate the velocity. We know the velocity goes with kinetic energy. Then we just made the kinetic energy the subject of the formula. All right, then obviously from what you know from this, if I'm making EK the subject of the formula, then this will cross over and becomes negative. So that's what we have right here. We have it there. This is the answer for it. It's negative. We have EP. EP is MGH. M is there. G is 9,8. H is here. So we can just quickly substitute. We did the substitution right here. So EK is mv squared over 2. Now we can see everything as m. So we can take m as a common factor and cancel it out. That's what we did. Now m is cancelled out. We are left with these two. G obviously is 9,8. H is 24. And WR is the 60. So we can make V the subject of the formula. Substitute right there and you are getting the answer. I hope it does make sense. The part that is very difficult is understanding this part. When you understand that, the rest is history. I really think it becomes very easy after that. Okay guys, I love you so much. Let's continue studying. If you didn't understand this, please go and listen to it again later again. It will make sense for you. Now let's go and do our last example. If time permits, I can do that bonus example. See you then. Welcome back, ships. Now we're moving to the last example for us, where we are talking about a car with a mass of 1,200 tons is at rest at the top of an incline of 1:30. The length of the incline is 62 meters. The frictional force is 2. Okay, the frictional force of 200 Newton is constant, that is uniform. The brakes are released and the car moves downwards due to gravity or to gravitational force only, and then onto a horizontal road. Calculate. Number 1, it is the velocity of the car at the bottom of the incline. Number 2, the force applied by the motor car on the horizontal plane. This is quite interesting. Number 3, the distance where the car will come to rest if it continues to travel on the horizontal road. Okay, so let's analyze this question. We'll analyze the places where we need to underline. For example, we will underline that we have the mass of the car 1.2 tons, and we know that it's at rest. That means U is equal to 0. We know that is at the top of an incline, so we do have an incline. We know that we have a slope. That means this is sine theta. The length of the incline is 2, so we know S, the frictional force. Then we have the frictional force, that is FR, and we know it's constant. When they saying it's constant, that means it's the same for the incline just as for the horizontal plane. We are using the same. That is why they have that word uniform. Then they're saying that the brakes are released and the car moves downwards. Now we know that it's moving downwards, so no wonder we have FA in the place of FT. So this is actually FT because it's moving downwards. It was supposed to be FT because it's moving downwards. It's FA. due to gravitational force only, and then onto a horizontal. That means it will reach the horizontal plane again. So in this question we have both information for incline and horizontal road. Then let's see, they say that we should calculate, number one, the velocity at the bottom of the incline, number two, the force that is being applied, number three, the distance. So that's what we are looking for. Okay, so how can we find the velocity with this information? We took down the data. We know that u is equal to 0. We know that this is the mass is there, u is equal to 0, sine theta is there, s is it. So we have u, we have s, we need v, we need t, we need a. I think t is hard to find, but a, we can find a. So since we can find a little easier, we can use the formula that has v, u, s and a. So let's go and look for it. U, v, a and t. Bah, it's not there. It's not what we want. V is what we want, u we have, a we can have, s we have. Yay! So this is the formula that we can be looking for. Or in fact, this is the formula that we can use. So let's go on and use that formula. So, but we still need a. How can we get a? We can get a from Fa is equal to Ma. Let's go back to our formula sheet. We can get a from this formula, but we do not have Fa, but we can have Fa obviously from this formula. Oh no, we are talking about the incline, so this will not be the one to give us Fa. But this maybe. But the thing is, we're not given Ft. So if we're not given Ft, we can just omit. We are going down, the slope is going downwards. That's what the question says. So Ft is not there. We'll just use this information because Ft is not there. So we have Fr, we have mg, so we can use it. So that will be the formula to find our acceleration, so that we can substitute from the formula for velocity. We need velocity. Let's substitute for m. Then we have that. After substitution, remember sine theta we said is equal to 1 over 30, so that is 1 over 30 right there. Let's do the substitution. Yes, that will be a for us. We have found a in that format. Then now we can be able to go to this formula sheet to find our v. There we go. We substituted. Then the place of u is 0. We have 2a, 2 times that times s. Therefore, this is the v for us. We have managed to find the velocity of the car whilst it is not driven. I like that part. Okay, then let's go to the second question. The second question wants us to find the force applied by the motor car on the horizontal road. Now, what we should consider, this guy is going down the slope. Can you see we do not have ft here? This is not ft, this is fa. So that means our fa will equal the negative fr, because remember when we were using our formulas that our remember when we're dealing with this formula, we noted that negative fa is equal to fb, or we can just simply say negative fa will be our fr. So we can just come back and apply the similar concept here. We'll say f is equal to fr, which will be negative 200, because it's going down the slope by itself. No acceleration is there, so the acceleration, no force is actually applied, so the engine is off, yet it is traveling downwards. So that is why we have it in that format. So we have our f equaling negative 2 for number 2. So the force applied by the motor car, not by the engine, on the horizontal road is this one. That means it's decelerating, it will end up stopping. That's why we have a negative 200. Okay. Then we have number 3, the distance where the car will come to rest if it continues to travel on the horizontal plane. So let's open the space for us to calculate this distance. Remember, this A is for the incline. Now we need to find an A for the horizontal line. This velocity is at the foot. That means now it becomes the initial velocity. So we have the initial velocity, which is this one. The final velocity is 0. We know it will stop because the question says it. It says will come to rest. Will come to rest. So if it will come to rest, that means v is equal to 0. Then the initial velocity is this one. The acceleration is not this one, because this is the acceleration for the slope. Now we need the acceleration for the horizontal road. So we still, because that's what they are talking about, the horizontal road. So we still need to find that acceleration in order for us to find the distance. And the formula for acceleration, as always, it is still fa is equal to ma. M we do not have, fa we do not have, but we can get the fa in this format as well. Okay, now here is in the horizontal road, so we can get it in that format, fa equaling ft minus fr. But we know that ft is not there, so we are left with fr, because ft is not given, so we take it as 0. So we have fr, so fa is equal to negative fr. So we can come back to this, then we will find our negative fr right there and find our a2. After finding this a, now we can come back to this formula again, because we have 0 as the final velocity, we have 4,454 initial velocity. We have our A, we have, oh, we need S, so that's what we can do, that's what we can have. We have all those ones, we have A, we only need S. Then we can do our substitution so that we may be able to find S. Okay, so this is what we have. Actually, that sign is negative, that's not positive. That sign is negative, so that when it crosses over it becomes positive, because our acceleration there was negative. In fact, let me quickly fix it. So now we can continue with what we're doing. So now we have changed it, we've made that that acceleration to be negative, so that we may get the real value for S. Therefore S equals to this one. So this is the answer we have for our S. Guys, this is all that we can do for today.